Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. It's 2 a.m., and a fintech startup's payment processing just ground to a halt. No one changed a firewall rule, no one deployed new code, but their primary outbound IP got blacklisted. Every VM in the subnet shares that IP, so the entire service is now unreachable. The cause? One chatty VM tripped a rate limit on a third-party API, and the blacklisted IP is Azure's default outbound access, something the team didn't even know existed. By the end of this video, you'll replace that fragile default with a static, scalable alternative that keeps your business off the blacklist. In this video, you're going to walk away with 3 concrete skills. First, you'll learn to pick a VNet address space that avoids overlap nightmares and to carve subnets that leave room for growth. Second, you'll know precisely when to staple a public IP directly to a VM and when to use a shared outbound solution instead. And third, you'll configure Azure NAT Gateway to handle anything from a handful of connections to 100,000 concurrent flows without a single port starvation. Let's start with the foundation, the VNet itself. The Azure Virtual Network, or VNet, is your private, isolated slice of the Azure cloud. Think of it as a portable data center, a logical container with an address space you define, like 10.0.0 or 0.16, and inside it you carve subnets to separate workloads. In Part 1, we toured a VNet. Today we're going to actually design one that won't back you into a corner 6 months from now. This diagram shows the core idea. One VNet, 2 subnets, each with its own CIDR block drawn from the parent range. One of the biggest networking mistakes happens before a single virtual machine is created: choosing the wrong IP address space. Imagine a company that has been using the 10.0.008 private address range for years in its on-premises data centers. A cloud administrator creates an Azure VNet using 10.0.016 because it looks familiar. Everything works perfectly until the company tries to connect Azure back to the corporate network using a site-to-site VPN. The connection fails because both networks use overlapping IP address ranges. Azure can't tell whether traffic destined for 10.0.525 belongs on-premises or inside Azure. The result is a costly network redesign. That's why the first rule of Azure networking is simple: never choose an address space that overlaps with any network you already have or any network you may need to connect to in the future. Whether you use 10.172.16 or 192.168 is less important than making sure every connected network has its own unique address space. Think ahead. A few extra minutes of planning today can save weeks of migration work later. CIDR notation looks intimidating at first, but the idea is surprisingly simple. The smaller the slash number, the larger the network. A24 contains 256 total IP addresses. A25 contains 128. A26 contains 64. A27 contains 32. Azure reserves 5 addresses in every subnet for its own platform services. That means a 24 provides 251 usable addresses. A 25 provides 123. A 26 provides 59. A 27 provides 27. These numbers matter because running out of addresses later usually means redesigning your subnet layout. When in doubt, leave yourself room to grow. IP addresses are cheap. Network redesigns are not. Quick question. How many IP addresses does Azure reserve in every subnet? The answer is 5. Those reserved addresses support Azure networking functions and cannot be assigned to your virtual machines. Whenever you size a subnet, always subtract those 5 addresses before calculating capacity. Here's a mistake many new Azure administrators make. They create a VNet with an address space of 10.0.0.0.16. Then, they immediately create one subnet that also uses the entire 10.0.0.16 range. Everything works until the application grows. Now, they need separate subnets for web servers, application servers, databases, Azure Firewall, Bastion, or private endpoints. There is no remaining address space. The only solution is to redesign the network. Instead, think about tomorrow while you're building today. Reserve subnet space even if those subnets stay empty for months. Planning ahead costs nothing. Rebuilding production networks can cost days of work. Professional Azure architects rarely design networks only for today's workload. Instead, they leave room for growth. You might create separate subnets for web applications, application services, databases, Azure Bastion, Azure Firewall, private endpoints, future workloads that haven't even been designed yet. Even if several of those subnets remain empty today, you've already reserved the address space. That flexibility becomes incredibly valuable as applications evolve. Remember, it's easy to deploy new resources into an existing subnet. It's much harder to redesign an entire production network because you ran out of address space. Quick review. Why don't we place every resource into one giant subnet? Because different workloads usually have different security requirements. Web servers may accept internet traffic. Application servers should usually communicate only with web servers. Database servers should accept connections only from application servers. Separate subnets make those security boundaries easier to implement using network security groups, Azure Firewall, and routing policies. Subnets don't provide security by themselves, but they give you the structure needed to build secure architectures. Every Azure subnet reserves 5 IP addresses automatically. Here's what happens inside a 24 subnet. The first address identifies the network. Several additional addresses are reserved for Azure Platform Services, including routing and DNS functions. The last address is also reserved by Azure. Those addresses cannot be assigned to your virtual machines. This is why a subnet with 256 total addresses only provides 251 usable addresses. Once you understand Azure's reserved addresses, subnet sizing becomes much easier. Let's test your subnet math. A 27 network contains 32 total IP addresses. Azure immediately reserves 5. That leaves 27 addresses available. So can you deploy 30 virtual machines into that subnet? No, you simply don't have enough usable addresses. Always calculate usable capacity, not total capacity. Every virtual machine in Azure receives a private IP address from its subnet. That private address allows communication inside the VNet and with connected networks like VPNs or ExpressRoute. A public IP is different. It allows resources outside Azure to initiate communication with your workload. Most production virtual machines do not need their own public IP address. Instead, organizations often place Azure Application Gateway, Azure Load Balancer, Azure Firewall, Azure Bastion, or other managed services in front of their workloads. This reduces the attack surface while making access easier to manage. When a workload only needs outbound internet access, Azure NAT Gateway is usually a better solution than assigning public IP addresses directly to every virtual machine. Azure offers two public IP SKUs, Basic and Standard. For new production deployments, Microsoft recommends Standard SKU. Why? Standard public IPs support modern Azure networking features such as NAT Gateway and Standard Load Balancer. They also support availability zones, stronger security defaults, and more predictable production behavior. Basic SKU still exists for compatibility with older environments, but most new Azure architectures should use Standard SKU unless you have a specific legacy requirement. When you're designing new infrastructure, Standard should be your default choice. Imagine your company's public website points to a virtual machine. The public DNS record sends customers to that server's IP address. If the public IP changes unexpectedly, customers can no longer reach your application until DNS is updated. That's why many production services use static public IP addresses. Static addresses remain consistent, making them ideal for DNS records, firewall allow lists, business partners, and production applications. Dynamic public IPs can be appropriate for temporary environments, testing, or workloads where the address itself doesn't matter. Before assigning any public IP, ask yourself one question. Does another system depend on this address remaining the same? If the answer is yes, choose a static public IP. Every virtual machine connects to Azure through a network interface card, or NIC. Think of the NIC as the VM's network adapter. The NIC, not the VM itself, holds the IP configuration. It receives a private IP address from the subnet and can optionally have a public IP resource associated with it. When the operating system sends traffic, it simply uses its assigned private IP address. Azure's networking platform handles everything else, including routing, address translation, security policies, and connectivity. One important point: you don't manually configure the VM's Azure IP address inside Windows or Linux like you might in a physical server environment. Instead, Azure manages the IP configuration through the NIC resource. That separation is one reason Azure networking is both flexible and highly scalable. Let's assign a static private IP. Open the Azure portal. Navigate to your virtual machine. Select Networking. Open the network interface. Choose IP configurations. Select the primary IP configuration. You'll notice the private IP allocation is currently set to dynamic. Change it to static. Azure automatically suggests the current address, or you can choose another available address inside the subnet. Select Save. Notice that we're changing the Azure resource, not editing the operating system directly. The VM continues using the assigned address while Azure manages the networking behind the scenes. Quick question: should every virtual machine receive a public IP address? No. Most production virtual machines never communicate directly with the Internet. Instead, organizations place Application Gateway, Azure Firewall, Azure Bastion, VPN Gateway, or load balancers in front of workloads. Only assign a public IP when direct inbound connectivity is actually required. Reducing unnecessary public exposure is one of the simplest ways to improve security. Here's a common design question: should every virtual machine receive a static private IP? Not necessarily. Azure's dynamic private IP allocation is stable for most workloads and greatly simplifies administration. Static private addresses are typically reserved for infrastructure that depends on predictable addressing, such as domain controllers, DNS servers, network virtual appliances, or systems referenced by fixed IPs. For most application servers, letting Azure manage address assignment reduces administrative overhead while still providing reliable connectivity. Choose static addresses because the workload requires them, not simply because they seem safer. Quick review. A domain controller should always remain reachable using the same private address. Should you choose dynamic or static? The answer is static. Predictable infrastructure services benefit from consistent IP addressing, while many application servers work perfectly well with Azure Managed Dynamic Assignment. Always choose the option that best supports the workload. Now let's talk about outbound internet connectivity. A virtual machine without a public IP still may be able to reach the internet. Historically, Azure could provide default outbound access for certain deployments. However, Microsoft now recommends using explicit outbound connectivity for production environments. That means choosing a service such as Azure NAT Gateway, Azure Firewall, or a public load balancer with outbound rules depending on your architecture. Why? Because explicit outbound connectivity gives you predictable behavior, better security, and a known public IP address that you control. Production environments should never depend on default outbound behavior. Imagine a business integrates with a payment provider. The provider allows requests only from approved public IP addresses. If your outbound address changes unexpectedly or isn't under your control, transactions begin failing immediately. With Azure NAT Gateway, your applications always leave Azure through one or more static public IP addresses that you own. Partners can safely list those addresses, making integrations far more reliable. Predictable outbound identity isn't just convenient. For many organizations, it's a business requirement. Every outbound internet connection requires source network address translation, commonly called SNAT. Azure NAT Gateway performs that translation automatically. Each public IP attached to a NAT gateway provides a large pool of SNAT ports that Azure uses to track outbound connections. Most workloads never come close to exhausting that capacity. However, applications that create very large numbers of simultaneous outbound connections or keep connections open for long periods can eventually require additional SNAT resources. The important design principle is this: plan for connection volume, not simply the number of virtual machines. High-scale applications generate connections, not servers. Here's how NAT Gateway works. Your virtual machines continue using their private IP addresses inside the VNet. When they connect to the internet, Azure sends the traffic through the NAT Gateway. The gateway replaces each private source address with one of its assigned static public IP addresses. Responses return to that same public IP. Azure automatically translates the traffic back to the correct virtual machine. None of the VMs need public IP addresses. Nothing changes inside the operating system. You simply gain secure, scalable, and predictable outbound connectivity for the entire subnet. One public IP attached to a NAT gateway supports a very large number of outbound connections. If your workload grows beyond that capacity, Azure allows you to associate multiple public IP addresses with the same NAT gateway. Each additional public IP increases the available SNAT capacity. The decision isn't based on how many virtual machines you have. It's based on how many simultaneous outbound connections your applications generate. Monitor actual usage before adding additional public IPs. Design based on measured traffic, not guesses. Quick review. Which Azure service is specifically designed to provide scalable outbound internet connectivity for an entire subnet? Azure NAT Gateway. Unlike assigning public IPs directly to virtual machines, NAT Gateway centralizes outbound connectivity while keeping workloads private. That's one reason it has become the recommended outbound design for many Azure production environments. Let's enable NAT Gateway. Open your virtual network. Select the subnet you want to modify. Locate the NAT Gateway setting. Choose the gateway you previously created. Select Save. That's it. Every eligible resource in that subnet now uses the NAT Gateway for outbound internet connectivity. No operating system changes. No VM reboots. No application modifications. The outbound path changes at the Azure networking layer, making the migration fast and low risk. Many Azure architectures use both Azure Load Balancer and Azure NAT Gateway. They solve different problems. Azure Load Balancer distributes inbound traffic across multiple virtual machines. Azure NAT Gateway manages outbound internet connectivity for the subnet. When both services exist together, inbound requests continue flowing through the load balancer. Outbound connections initiated by the virtual machines use the NAT Gateway. Each service performs a separate networking function, allowing the architecture to scale cleanly in both directions. Every network device eventually closes idle connections. Azure NAT Gateway also uses an idle timeout. Most web applications never notice this because they create short-lived connections. However, applications with long-running sessions, large data transfers, or infrequent communication may require a longer timeout configuration. If users report connections unexpectedly closing after periods of inactivity, reviewing idle timeout settings should be one of your troubleshooting steps. Always configure timeout values based on the application's communication pattern, rather than using the same setting everywhere. Let's review one of the most important scaling concepts. What determines whether you need additional public IP addresses on a NAT gateway? Is it the number of virtual machines? No. The real factor is the number of simultaneous outbound connections your applications create. A small number of highly connected services can consume more SNAT resources than hundreds of lightly used virtual machines. Always measure actual connection patterns before scaling. Let's automate the deployment. Using the Azure CLI, you'll first create a standard SKU static public IP. Next, create the NAT Gateway resource and associate the public IP. Finally, associate the NAT Gateway with the target subnet. Once that association is complete, eligible resources in the subnet automatically begin using the NAT Gateway for outbound internet connectivity. This is one of the reasons infrastructure as code is so powerful. The deployment is repeatable, consistent, and easy to version alongside the rest of your Azure environment. PowerShell follows the same overall process. Create the public IP, create the NAT Gateway, associate the gateway with the subnet. The implementation language changes, but the architecture stays exactly the same. Whether you prefer Azure CLI, PowerShell, Bicep, or Terraform, understanding the networking concepts is far more important than memorizing individual commands. Production networking doesn't stop after deployment. Monitoring is just as important. Azure Monitor provides metrics that help you understand how your NAT gateway is performing. Track connection counts, SNAT utilization, throughput, and other available metrics. Configure alerts before resources become constrained. Good monitoring allows you to scale proactively instead of reacting after users begin experiencing connectivity problems. Healthy production environments are monitored continuously, not just during outages. Like most Azure services, NAT Gateway has operational costs. You'll pay for the gateway resource itself as well as data processed through the service. Pricing varies by Azure region and may change over time, so always verify current pricing using the official Azure pricing calculator before estimating project costs. When planning an architecture, consider networking costs alongside compute, storage, monitoring, and security services. Cloud architecture is as much about financial planning as it is technical design. Quick review. Users report that long-running but inactive connections occasionally disconnect. One possible cause is an idle timeout somewhere along the network path. Timeout settings exist in many networking devices and Azure services, including NAT Gateway. When troubleshooting intermittent disconnects, always consider application behavior together with network timeout settings. Business-critical applications often require highly available outbound connectivity. Azure NAT Gateway supports deployment across availability zones when designed appropriately. This helps improve resiliency if a single availability zone experiences an outage. High availability isn't just about virtual machines. Every networking component, including load balancers, gateways, firewalls, and outbound connectivity, should be considered during architecture design. Azure Firewall and Azure NAT Gateway are complementary services. Azure Firewall focuses on security. It inspects, filters, logs, and controls network traffic according to organizational policy. Azure NAT Gateway focuses on scalable outbound internet connectivity. Some enterprise environments use both together. Azure Firewall enforces security policy. NAT Gateway provides large-scale outbound address translation and predictable public IP addresses. Each service solves a different networking problem. Imagine managing 50 application servers. Would you rather secure 50 public IP addresses or none? Most organizations choose the second option. Instead of exposing every server directly to the internet, they keep workloads private and publish only the services that require external access. Azure NAT Gateway allows private workloads to reach the internet without exposing inbound connectivity. Reducing unnecessary public exposure is one of the simplest ways to strengthen your security posture. Here's a common point of confusion. A virtual machine may use NAT Gateway for internet-bound traffic, while also accessing Azure storage using a service endpoint. These are not competing technologies. Service endpoints optimize connectivity between a subnet and supported Azure platform services by extending the subnet's identity to those services across the Microsoft backbone. Internet-bound traffic continues using the NAT Gateway. Azure platform traffic follows the appropriate service path. Understanding where traffic actually flows is an important networking skill. A virtual machine cannot reach an Azure storage account protected by a service endpoint. What should you verify first? Confirm that the service endpoint is enabled on the correct subnet and that the storage account's networking configuration allows traffic from that subnet. Many connectivity issues are configuration problems rather than networking failures. Migrating from default outbound connectivity to Azure NAT Gateway is straightforward. Deploy the NAT Gateway. Associate it with the target subnet. Verify outbound connectivity. Confirm the new public IP address. Then update any external firewall, allow lists if required. Because the change occurs at the subnet level, applications usually require little or no modification. Simple migrations like this are one reason Azure networking is so flexible. Let's put everything together. Your web tier receives inbound requests through Azure Load Balancer or Application Gateway. Application servers communicate privately inside the VNet. Database servers remain isolated from direct internet access. Every subnet shares predictable outbound connectivity through Azure NAT Gateway. The result is a clean architecture with controlled inbound traffic, scalable outbound connectivity, and minimal public exposure. This pattern appears in production Azure environments around the world. As applications grow, monitor outbound connection patterns carefully. If workloads require additional SNAT capacity, Azure allows multiple public IP addresses to be associated with the same NAT gateway. Use Azure Monitor metrics to understand actual utilization before scaling. If different workloads have significantly different outbound requirements, consider separating them into dedicated subnets with their own NAT gateway. Design networking around application behavior rather than assuming one size fits every workload. Every architecture decision has financial implications. Outbound internet traffic, cross-region communication, and certain networking services may generate additional charges. Azure Cost Management helps identify which resources generate networking costs over time. The goal isn't simply to minimize spending, it's to understand where costs originate so you can make informed architectural decisions. Successful cloud architects balance performance, security, reliability, and cost together. One final review. Which direction of internet traffic most commonly generates Azure bandwidth charges? Outbound traffic leaving Azure. Understanding that simple principle helps prevent many unexpected cloud bills. Let's step back and look at the complete design. A carefully planned address space, purpose-built subnets, private IP addressing, minimal public exposure, scalable outbound connectivity through Azure NAT Gateway, monitoring, cost awareness. This isn't just a collection of Azure services. It's a networking architecture designed for real production environments. Everything you've built today can be deployed using infrastructure as code. Whether you choose Bicep, ARM templates, Terraform, or another automation platform, the goal remains the same. Define your networking architecture once. Store it in source control. Review changes. Deploy consistently across development, testing, and production. Modern cloud engineers automate infrastructure because consistency reduces mistakes. Today you learned 3 essential Azure networking skills. First, how to design VNets and subnets that support future growth. Second, how to choose between private IPs, public IPs, and Azure NAT Gateway for different workloads. And third, how scalable outbound connectivity supports secure, predictable production architectures. These are practical skills you'll use whether you are preparing for the AZ 700 exam or designing enterprise Azure environments. One final question. If a production subnet needs predictable outbound internet access without assigning public IPs directly to virtual machines, which Azure service should you choose? Azure NAT Gateway. If you answered that immediately, you've understood one of the most important networking design decisions in Azure. Knowledge becomes valuable only when you apply it. Create a new virtual network. Build multiple subnets. Deploy 2 virtual machines. Configure Azure NAT Gateway. Verify the outbound public IP. Then compare that design with one using direct public IP addresses. Nothing reinforces networking concepts faster than building them yourself. You've now mastered the networking foundation inside a single VNet. Next, we'll connect multiple virtual networks using VNet peering, hub-and-spoke architecture, and gateway transit. These designs are used throughout enterprise Azure environments and form the backbone of modern cloud networking. I'll see you in Part 3. Remember, cloud architects aren't created by memorizing documentation. They're created by designing, building, testing, troubleshooting, and improving real environments. Take one concept from today's lesson. Build it, break it, fix it. Then document what you learned. That's exactly how experienced Azure engineers develop their expertise. Thanks for watching Hired in IT. We'll see you in the next lesson.